Hello, and welcome back. Okay, so we're going to be looking at another application of a diode. Okay, so we use diode as a component in DC power supply. All right, so as a component of DC power supply, diode acts as a voltage rectifier. Okay, so a diode acts as a voltage rectifier. What does it do? What is a rectifier? Okay, now a rectifier is actually a device, a component that converts an alternating voltage, okay, an alternating current. As you can see here, it's an alternating current. It converts it to a direct current, but such direct current is a pulsating direct current, okay, not a direct current that is stabilized, but a pulsating direct current. So now this is a typical schematic of a diode acting as a rectifier. Here I have alternating current source, okay, voltage being supplied through a transformer. This is a transformer. This is the primary side of the transformer, okay, where that is the input, and this is the secondary side of the transformer that supplies the output. Now, in most cases, okay, this is a step-down transformer, like your power supply that you use in, of course, charging your phone or whatever uh, DC device you power. Okay, you discover that most of those devices uses a very small voltage. Meanwhile, the supply in your house is like 220 volts, but you need most of those devices and electronic devices need 10 volt, some need 5 volts, some need 12 volts. So there is need for a transformer to step down the 220 volt, okay, from your main supply to something like 12 volts, okay, depending on the rating of the transformer on the or the need of the voltage, okay. So in this case now, this transformer has stepped down this 20 volt to 12 volt AC, all right, that need to be rectified. So now this 12 volt now is going to be an input to this diode that is going to be used as a rectifier. So now, how does a diode function as a rectifier? Okay, due to the operation of a diode, you know that a diode can also function as a rectifier. What does it do as a rectifier? A diode, you know very well that only allow current that is actually in the forward direction, okay? Only operate in a forward bias mode. When you forward bias a diode, okay, it will actually allow the flow of current. But when it is being reverse biased, okay, it will block the flow of current. So which simply means that for an alternating current that is supplied to a diode, remember alternating current is a current that actually changes magnitude and direction at the same time. At one point it is positive from this diagram. At one, this side of the current is positive and this side is negative, okay? So diode can only allow the positive part of the current to pass through it, or the voltage. Remember, as the current alternates, the voltage also alternates, okay? So now diode only allow the positive parts, okay? Why? Because diode actually operate at a forward bias, in a forward bias direction. So now the part, once the cycle actually enters into the negative part, what happened? The diode blocks it, okay? It will not allow it as an output. So that is why you can see this is the connection. Now this is my load. So this is the graph of the input voltage, the Vin, having circles, positive and negative circle, okay. Now when I pass this voltage across the diode, what happened? Diode will cut out the negative part of that circle. So we simply mean that's this negative part of the circle, diode will cut it out, okay, will block it. So only allowing the positive part, the only positive voltage, okay. And of course this positive voltage is the DC voltage, but the DC voltage is not stabilized, but it's still positive, okay, all through. So the negative part has been cut out. So you discover that this type of rectifier is not efficient. Why? Because it will reduce the efficiency of the DC. Why? Because some of the voltage supply has been cut out, okay. So efficiency will definitely be reduced. So this is the simplest form of rectification, okay, or rectifier, and that's what we call it half wave rectifier. As you can see, it's half wave, so it only allows half of the wave, okay. The other half, remember, a wave is made up of two half, the positive and negative, okay. So you only allow the half of it to pass through the diode, to pass through to the load as an output. So this is half wave rectifier. This is how the schematic diagram, okay, is and of course I've described how it works. Then we now have what is called the full wave rectifier. Now this is the most efficient form of rectification. Okay, full wave. Why? Because in full wave, the entire cycle is being rectified. Now this is how this is actually being constructed. For a full wave rectifier, we use two diodes. Okay, let me call this diode D1. Let me call this diode D2. Okay, so this diode, why am I using two diodes? So that each of the diode will function for each of the half wave, both the positive and the negative. Okay, but now the question is, for the one that function in the negative direction, well, will it not output the negative voltage to my output? Since all I need is just positive, okay, I'll tell you no, it will still output positive. That is why for this schematic, you discover that with the kind of transformer I use, okay, the transformer that is used here is known as a center tap transformer. Let me illustrate what I mean by a center tap transformer. It's a transformer like the previous transformer I actually showed you. Okay, remember transformer, this is the input, right? Now I have the output of the secondary winding. Okay, so now this secondary winding now is now being center tap to give me two voltage output. One, okay, so the center tap now is actually is grounded, so I have two voltage output. All right, one output, okay, one output is taken from, so this is my diode. Let me just put my diode, please pardon me. Okay, so it's giving me two outputs. So one output is taken from the very first diode with the center tap. The center tap is common. Okay, it's a common point with the output of the first diode. Okay, so that means at this point now I have a voltage, as you can see here. So this is what I'm doing. So this diode is center tap. So that's a center connection. Okay, so I'm taking a voltage with respect to the first diode, and that I'm taking a voltage, okay, first with respect with the first diode and the center tap connection, and secondly another voltage I will still take it from the output with respect to the second diode and the center tap. So the center tap is common, and that is why it is always grounded. Okay, I'll tell you more about the ground. It's a common connection. So which simply means that, so what is the essence of the center tap? This center tap now will actually deliver two voltage. All right, as you can see here, this two voltage that is 180 degrees out of phase. One is positive circle, okay, where the other one is actually negative circle. You understand? They are 180 degrees out of phase. When this one is positive, is moving a positive circle, the other part of the voltage, okay, from of the other half is moving in the negative circle. So now how does, what is going to be the output of this power supply? Okay, let's see what will be the output. Let's see how this power supply will actually output. Okay, so now when the voltage is actually positive, this very first diode D1 here actually conduct. Remember, we've talked about this. Okay, it will conduct. So at the point where this one is, the voltage is positive, the diode D1 conducts. So we'll have that positive circle. Now, at the point where the voltage is negative, the diode D1 is no longer conducting, it has now blocked. Okay, it is being reverse biased. Okay, so at that point D1 is not conducting, so D1 will not give any output. So the only output, D1 gives only outputs when the voltage is voltage, okay, is actually positive. So you only give that output of the first circle. Let me draw it here. So when when it is in the when the voltage across it is in the negative circle, it blocks it. So you only give this, okay. So now for the when the voltage of the D1 passing across that's passing across the D1 is negative. Remember, okay, if you look at D2, the voltage across the D2 at that particular moment, it is now positive. Why? Because the voltage across D1 and D2 is 180 degrees out of phase, okay? When one is positive, the other one is negative. When one is negative, the other one is positive, okay? So at the point where D1 now is now having a negative voltage, remember D2 is now having positive. And because D2, the voltage across D2 is positive, it conducts, okay? So at this point now, D2, at this second circle, this is the second part of the circle, okay? So I have to shift it a bit. So D2 actually conducts. This is when D2 conducts, okay? So if I combine it, okay, the flow of D1 with the conduction of D2 at the two circle, you discover that there is no lapses, okay? So after this is the overall output. This is for D1, okay? This is when D1 actually conducts. So at the point where D1 supposed to be negative, D1 is no longer conducting. Now D2 is conducting in a positive direction. So for a full wave rectifier, you discover that the lapses that we had before, if I can still get the lapses here, this lapses here, okay, is not there, okay? So that lapses is now occupied by a positive circle, okay, from the second diode. So this is this is the graph of a full wave rectifier, full wave. And you discover that this is more efficient, okay? So this will give more efficient, this will give more power as more direct current power compared to the half wave rectifier. And we are going to look at the parameters, the formula, the equation that is used to distinguish between the output of a half wave rectifier to the output of a full wave rectifier. We'll do that in the next video. All right, so please take your time, understand the logic behind these two type of rectifier, full wave rectifier, and of course a half wave rectifier. See you in the next video. Thank you very much.